Hey guys, welcome back. So today we're going to be covering limits at infinity, infinite limits, and indeterminate forms. So the big idea here is what happens when x or f of x gets really, really large. So we're talking huge numbers that approach infinity. But before we jump in, it's important that we make a quick distinction. Infinity isn't a number, it's a concept. And so when we're dealing with, infinite limits, limits at infinity, all of these things, we have to remember that we can't just plug in infinity, and that limit laws like adding, subtracting, multiplying, dividing don't necessarily apply because we do those things, those operations with numbers, and infinity is not a number. And so that's just a quick, wrap up of how we need to think about infinity. So let's jump right in and start with an example. Example 1. Okay, so I'm going to draw a graph and then give you the equation we're going to work with. It's kind of a rough estimate of how this function looks, just so we can have a visualization in our head. Okie dokie. So we have that g of x is equal to x over 1 plus x squared. And we're asked what is the limit as x approaches infinity of g of x. And so the big idea here is we're asking what happens as x goes to infinity, gets larger and larger without bound, what happens to g of x. And so again, it's important that when we're dealing with infinity, we have to deal with things a little bit more carefully. And so when we write the limit as x approaches infinity, we're not talking about way far down the number line that x is going to reach infinity. X is never going to reach infinity, because we're really asking here, when the limit as x approaches infinity, what happens as x grows larger and larger without bound? What happens to the function? Okay, so I'm going to draw us a table. We can better visualize this. We have x, we have g of x. Okay, so we have this table, we have this chart, we have x, we have g of x, and we're going to start to plug in numbers and just see how the function behaves. So we have 10, g of x is going to be 0.099. We have 100, 0.010, and etc. So we see as x gets bigger and bigger, g of x looks like it's getting smaller and smaller. And so we can pretty safely say that the limit as x approaches infinity of x over 1 plus x squared is equal to 0. And if we were to ask if it approaches negative infinity, it also looks like it approaches, oh, my bad. Okay, so when I say infinity, when I was talking about how we should think about infinity, I'm also implicitly implying that we're also talking about negative infinity. So I might not explicitly say positive infinity or negative infinity, just assume that I'm talking about both of them, unless I explicitly say I'm only talking about positive infinity or negative infinity. Okay, we're going to move on to our second example now. Okay, example 2. Okay, so we're asked to prove that the limit as x approaches infinity is indeed, the limit as x approaches infinity of x over 1 plus x squared is indeed equal to 0. So in the last example, this was more of a conceptual idea, so we can start getting our feet wet with limits at infinity. But this time we're actually asked to prove, mathematically, analytically, computationally, or whatever, that this limit is actually equal to 0. So we're asked, how do we do that? Okay, so I'm going to introduce a powerful technique for limits at infinity that will help you just figure out what the actual limit value is. Okay, so when we have, I'm just going to rewrite this. When we have limits at infinity, a really cool thing that we can do, because again, we can't really plug this number in, so we have to get a little bit creative. So what we can do is actually divide the numerator and the denominator by the highest power found in the denominator. So in this case, it'll be x squared. Because x squared is the highest power in both the numerator and the denominator. So we can also use our limit laws and just break this up. Alright, so then we can do some quick simplifications. So we have x over x squared, so we just have 1 over x, 1 over x, and then the limit as x approaches infinity of 1 over x squared plus 1. Okay, so after we do that, we'll get 0 for the top limit, and then 0 plus 1. So 0 divided by anything is just 0. Okay, so this was an example of how you solve limits at infinity. What you want to do is divide the numerator and the denominator by the highest power found in the denominator, which in this case was x squared. And what that does is it actually cancels out some things and it just makes it easier to solve. Okay, so you might be asking, okay, that's great, but we didn't really cover why the limit as x approaches infinity of 1 over x is 0. We just kind of skipped through it, and you're correct. So let's take a moment to describe what that's actually doing. Okay, so we're used to being able to just plug in numbers when we take limits, right? But infinity is different, and I said you can't really plug it in. We have to think about it as a concept because it's not a number, and that's correct. Okay, so instead of directly plugging in numbers, we're just going to plug in larger and larger values for x. And so it's kind of a workaround, so we can see how the function behaves, but not necessarily have to plug in infinity because we can't do that. Okay, so this is the 1 over x, and we're plugging in larger and larger values for x as a sort of a workaround for not being able to exactly plug in infinity. So as you can see, as we plug in larger and larger values of x, f of x gets really small. And we have to think about what's happening when we plug in any number over a really large number. This is division, right? And so we're having to split this small number into larger and larger increments, right? And so it gets closer and closer to 0. And is it really exactly 0? No. But as you get really far out, these really huge numbers, it looks like 0. And so mathematicians have just said, okay, it's close enough to 0, it's 0. And so that's why the limit as x approaches infinity of 1 over x is 0. So I hope that gave you a little bit more clarity as to why that's the case. Okie dokie, so we're going to do another example just so we can get a better understanding of how limits at infinity work. So we're going to take the limit as x approaches infinity of x squared divided by x minus 5 times 3 minus x. Okay, so we're just going to work through this kind of methodically and break it into pieces. So the first thing we can do is multiply out or FOIL this denominator so we can get a better understanding of the highest power in the denominator. So we're going to do first, so 3x minus outer, x squared inner, 5x plus last, oh, oops, my bad, inner is negative 15. Minus negative 15 plus 5x. Okay, so we can do a little bit of simplification, so let's do that. Limit as x approaches infinity of x squared over negative x squared plus 8x minus 15. Okay, so now we can clearly see that the highest power in the denominator is that x squared. So we can divide the numerator and the denominator by x squared. So limit as x approaches infinity of x squared divided by x squared over limit as x approaches infinity of negative x squared divided by x squared plus 8x divided by x squared minus 15 divided by x squared. So we have x squared divided by x squared, which is just 1. And then we have a limit as x approaches x squared, or negative x squared, so we have negative 1 plus 8 over x, and then minus 15 x squared. So similarly to the first example we have these numbers over infinity, which are just getting crushed down when we divide these pretty small in comparison numbers to these really, really large, even 100 million, all these big numbers. And so they're going to get crushed down to 0. So we're going to end up, 1 is just going to stay the same because it's a constant. So we're going to have the 1 over the negative 1, and that's just going to be equal to negative 1. So if we were to write our final answer out, we'd say that the limit as x approaches infinity of x squared over x minus 5 times 3 minus x is equal to negative 1. That'd be an example, worked example of how you would do limit at infinity. Okay, so now we're going to work on a new definition for horizontal asymptotes. Okay, so to say that the limit as x approaches infinity equals L, where L represents a finite number, this is the abbreviation for number, then the line y equals L is a horizontal asymptote of f. And then similarly, if the limit as x approaches negative infinity of f of x equals m, where m is a finite number, then the line y equals m is a horizontal asymptote of f. Okay, so what does this mean? This means that as x approaches infinity, the function is going to equal some finite number. So as x grows larger and larger without bound, y is getting closer and closer to a certain value. And so we do this, we find out these horizontal asymptotes. Remember, we can't quite plug in infinity because infinity is not a number. So we work around that by plugging in larger and larger values of x, or smaller and smaller values of x for the negative infinity to see what the function approaches. Okay, so I'm going to do some quick illustrations so you can get a clear picture of what these horizontal asymptotes look like. Okay, so you might have something that kind of looks like this. This is a line y equals L, and you might have something approaching, the function approaching the horizontal asymptote from below. And then similarly, you might have a function that kind of looks like this, approaching it from above. And then a third case that you might see is where you have that horizontal asymptote and it kind of just oscillates, which means it doesn't quite reach a function value, it just kind of hovers around it. So we have reaching from below, above, and then oscillating, not quite reaching the horizontal asymptote. And just a quick note, the graphs may have more than one horizontal asymptote. And then as we saw in the last illustration, the graphs may cross the horizontal asymptotes. Okay, so now we're going to move on to infinite limits. So the first part of the video we talked about what happens as x grows larger and larger without bound, what happens to the function. Now we're going to see what happens if the opposite is true. What happens if g of x, or f of x, is approaching a really, really large value without growing without bound? What happens to x? Okay, so infinite limits are those that have a value of positive and negative infinity where the function grows without bounds as it approaches some value a. So I'm just going to write a quick example to illustrate that, and then we'll jump right in. Okay, so we have this vertical asymptote here, and then, okay, so we're told that f of x is equal to 1 over x minus 1 squared. And we're asked to find the limit as x approaches 1 of this function. The limit as x approaches 1 of 1 over x minus 1 squared. Okay, so the first thing we're going to have to do is break it up into the left-hand limits and the right-hand limits because it did not specify. So I'm going to kind of just do this. So we'll have the limit as x approaches 1 from the positive side of 1 over x minus 1 squared, and then we'll have the limit as x approaches 1 from the negative side of 1 over x minus 1 squared. Okay, so if we look, we're just going to do, a graphical representation of this infinite limit. So if you look at the left-hand side, or the right, the positive side approaching from the left-hand side, my bad. We look, okay, so it seems like it's just going straight up to infinity. It's not reaching a particular value because, this horizontal asymptote extends as far as we want it to in both directions. And then similarly for the other limit, it goes right up to infinity. So we can say that since the left-hand limits and the right-hand limits are both equal to infinity, or both approach infinity, we can say that the limit as x approaches 1 of 1 over x minus 1 squared is equal to infinity. Okay, so I just wanted to, I'm just going to rewrite this function real fast. Okay, so if we think about it, what we're doing when we write out these limits So we have the limit as x approaches 1 from the positive side and the negative side. So from the positive side, it's going to be just slightly bigger than 1. So we're going to have, like, let's say 1.0001, and then this is going to end up being a positive number. And then similarly, if we had approaching from the negative sides, so 0.99999, it's also going to be a positive number because it's squared. And then we have to think about, what happens to this 1 as it's being divided by that really small number. It's going to shoot up to infinity. So just for all of these problems, you want to have a good sense of numerically what's happening to the function. A lot of times in these calc classes, you're not going to be allowed to have a scientific calculator or even any calculator. So it's a really good idea for you to get a good grasp of what these functions are doing and then just be able to play with the numbers a little bit in your head. So we're going to work to develop that a little bit. Okay, so I took a second to write down how do we find infinite limits without a graph. Okay, so the first step is that we're going to want to find values that are close to a, which is just the value, I just gave it a variable name, just the value that we're looking for as x approaches. So we want to do that coming from the left and the right side. And that's just to see how the function is behaving coming from either direction. Okay, then we want to observe the behavior. So either the function is going to get really big, going to infinity, or really small, going to negative infinity. And then it's going to either get positive or negative. And then the third step is to analyze the results carefully. So what do we find from what the function is doing from the left-hand side, from the right-hand side? Are they the same value? Kind of things like that, so we can make an educated decision about the function's value as the limit. Okay, so now we're just going to get some more practice with doing these infinite limits and analyzing them analytically. So we have the limit as, example 2. So the limit as x approaches 4 of 5 divided by 4 minus x. So again, we're going to split that up into our left-hand and right-hand limits. So the right-hand limit as x approaches 4 from the positive side of 5 divided by 4 minus x. Then the limit as x approaches 4, negative side, 5 divided by 4 minus x. Okay, so let's start with the left-hand limit. So we're going to choose a value that is not 4 because, again, the first step should always be to plug in the number. So if we plug in 4, it'll be 5 divided by 0, and you might have been told, when you're younger that you can't divide by 0. So we're going to have to find another way to work around that. So we do this by, let's pick a value that's really close to 4, but just slightly less. So we can choose 3.999 as our value for the left-hand limit. Okay, so now we're going to have 5 divided by 4 minus 3.999, and that's close to 5,000. So that's large, check, and positive. Another check. Okay, so similarly, we're going to choose another value for something that's just a little bit bigger than 4, so we can choose 4.40001. Okay, so we have 5 minus 5 divided by 4 minus 4.0001, and that's approximately negative 5,000. So this one is small, check, positive, or negative, sorry. Negative. So with a good degree of certainty, we can say that the limit as x approaches 4 from the negative side is going to be equal to positive infinity, and then the limit as x approaches 4 from the, I flipped those. From the positive side is going to be negative infinity, which means that the limit as x approaches 4 of 5 divided by 4 minus x equals, does not exist. Okay, so hopefully that example gave you a little bit more of a better idea of how you can strategically choose the values for your limits. Okay, so a new definition for vertical asymptotes. So similarly to how limits at infinity gave us horizontal asymptotes, infinite limits are going to give us vertical asymptotes. So if limit as x approaches a from the positive side of f of x equals plus or minus infinity, or the limit as x approaches a from the negative side of f of x is equal to plus or minus infinity, then x equals a is a vertical asymptote. So I'll just give you 3 quick examples of how that could look. Okay, so we have vertical asymptote at x equals 0, and that could shoot off to positive infinity. We have an example at x equals 0 of something that could shoot off to negative infinity. And then we could have one like in our last example, where one goes to positive infinity, or one side goes to positive infinity, and another side goes to negative infinity, so the limit would not exist. I just want to give a quick visual representation of how these vertical asymptotes might appear. Okay, so to wrap up talking about vertical and horizontal asymptotes, I'm going to create a quick chart. I'm going to use HA for horizontal asymptote and VA for vertical asymptote. Okay, so the limit as x goes to positive or negative infinity of f of x is going to equal L. So x is going to go to positive or negative infinity, and then y goes to some fixed value. So the one to remember for this one is just y is equal to L slash m. Then on the other hand, for vertical asymptote, the limit as x approaches a of f of x is equal to positive or negative infinity. So x goes to some fixed value, but y goes to positive or negative infinity. And so the one to remember for this one is x is equal to a. This is just a quick, summary of the vertical and horizontal asymptotes that we've seen. Okay, so now we're going to wrap up the video with indeterminate forms. So we've actually already seen an indeterminate form, the form 0 over 0. So we dealt with this indeterminate form by doing things like multiplying by the conjugate, canceling out, factors, and other, algebraic ways of manipulation to ensure that we didn't have to deal with this. So we didn't necessarily know it was an indeterminate form, we just knew it didn't quite work out. But this is actually one of the 7 indeterminate forms. So the main thing we want to think about if we see an indeterminate form is to just do more algebra. Find a way to algebraically manipulate the expression so that we can figure out the limit's value. And so an indeterminate form is actually a form of a limit that doesn't tell us if the limit exists or what the limit's value is. So we want to do everything we can possibly do to eliminate that. And so in the next video, I'm going to give you some techniques about how to actually deal with these 7 indeterminate forms. So we have 0 over 0, infinity over infinity, 0 times infinity, infinity minus infinity, 0 to the 0th power, infinity to the 0th power, and infinity to the 1st power. Okay, so I just went ahead and wrote out the common types of limits you might see. So the first type you might see is 0 over non-zero numbers. So that could take the form of just 0 over 7, and anything divided by 0 is just 0. Second, you might see a non-zero number over 0. So let's say it's like 7 over 0. So that's going to, depending on the limit, be infinity, negative infinity, or does not exist. A 0 over 0, like we covered in the indeterminate form section, is just going to be a do more algebra. And similarly, infinity over infinity is not equal to 1. It's another do more algebra, another indeterminate form. And then the last type you might see is a number over infinity. And similarly to the fact that the limit as x approaches infinity of 1 over x is equal to 0, a non-zero number over infinity being divided by increasingly larger and larger values is just going to crush it down to 0. So any non-zero number over 0 or over infinity, my bad, will be 0. And so last thing we're going to cover is just special limits to memorize. The first one is going to be the limit as x approaches 0 of sine of x over x. That's just going to be 1. And number 2, the limit as x approaches infinity of c over x squared is going to be 0, where c is a real number. Okay, so the limit as x approaches 0 of sine of x over x is just 1. I will link a proof down in the description if you're interested as to why that is, but that's just a good one to memorize. And then number 2, the limit as x approaches infinity of c over x squared is equal to 0. Going back to the one where we talked about the limit as x approaches infinity of 1 over x is equal to 0. If you have a real number and it's just getting divided by infinity, increasingly larger and larger values, it's just going to get crushed down to 0 again. So I hope you guys learned something from this video. Again, if you have any questions, please leave them down below in the comments and I will do my best to answer them. Thank you.